Let us talk about saturation temperature and saturation pressure. Now to understand this, let's take the example of boiling of water. Now we have seen the statement that water boils at 100 degree Celsius. Now this is a statement which is not right. It is an incorrect statement. The correct statement is that water boils at 100 degrees Celsius at 1 atmosphere's pressure. So now this statement is a correct statement. The only reason the water starts to boil at 100 degrees Celsius is because we hold the pressure constant at 1 atm. So 1 atm or is equal to 101.325 kilopascals. Okay, so because we hold the pressure or we keep the pressure constant, that is why the water starts boiling at 100 degrees Celsius. Now if the pressure of the water was raised to, let us say, if the pressure of the water was raised to 500 kPa. Okay, now how you raise the pressure, it is immaterial. Upon raising the pressure, let us say the boiling point at which the water started to boil, okay, it now becomes 151.8 degrees Celsius. Okay, so this means that there is a direct correlation between the temperature at which the water boils and the pressure at which the water starts to boil. Alright, so this means the temperature at which water starts boiling, it depends on the pressure. Therefore, if the pressure is fixed, so is the boiling temperature. Alright, so if we keep the pressure, let us say, at 500 kPa only, the boiling point of the water will also stay at 151.8 degrees Celsius. Alright, now at a given pressure, the temperature at which a pure substance changes phase is called saturation temperature. So this is a definition worth noting down. So let's define the temperature of saturation. That is, it is the temperature at which a pure substance, now this temperature is for a given pressure, for a given value of pressure, okay, at which a pure substance okay, it starts to change its phase, alright, so that temperature we call the saturation temperature. Now similarly, and on the similar lines, we can define the saturation pressure. Now saturation pressure is for a given temperature. So at a given temperature, the pressure, so now this is the definition of the saturation pressure. Now this pressure is for a given temperature. For a given temperature at which the pure substance changes phase is called saturation pressure. So pressure at which a pure substance changes phase is called the saturation pressure or Psat. Alright. Now if you take the case of a very common example, that is of water. So at a given saturation pressure, or you can say at a given pressure, I would say, not a saturation pressure. Okay, so at P is equal to 101.325 kilopascals. Alright, the saturation temperature is equal to 99.97 degrees Celsius. So we take it to be almost 100 degrees Celsius. Okay, so this is how you have to define your saturation temperature, because it corresponds to a particular value of pressure. Alright, and similarly at a temperature of 99.97 degrees Celsius, alright, the saturation pressure would be 101.325 kPa. So the saturation pressure over here is also as per a given value of temperature. Now if you look at the TV plot given to you, that is the temperature volume plot, now you can plot the states that were told to you in the previous video, in which we talked about the various kinds of states. So let us say this is state number 1, this is state 2, this is state 3, this is state 4, and this is state 5. Now state 1 to 2, so this can be, this is called the compressed liquid state. So compressed liquid state. Okay. Then you have the saturated mixture state. So if you remember this, saturated mixture state. Alright. And then we have the superheated state. Okay, so this is the superheated vapor. Superheated vapor. And all this happens at a pressure of 1 atmosphere. So you can see the correlation again on a graph with the pressure and temperature. Now let us say we have a solid. So let's take a solid. So this is the solid. Okay. Now when you heat it, that is, let us say we are heating it by putting a flame beneath it. So we are heating it. So we're basically melting it, isn't it? So melting means converting a solid into a liquid. That is what we all know. So let's make a liquid out of this solid. So it's a blue colored solid, so you'll have a blue colored liquid, isn't it? So that's how you'll understand. So this is melting, okay, which is a phase change. Okay, now if you still keep on heating it, now you're heating the liquid below it. Alright, and as you heat it, this liquid will now convert into vapor. So let's take, you can say, a vessel. So this is a vessel in which I have to store my vapor. So you have blue colored solid, you had blue colored liquid, and similarly you will have blue colored vapors. Alright, so this is how the vaporization process takes place. So this is the vaporization. Okay, now it takes a lot of energy to melt a solid or vaporize a liquid, because you can see that there is some energy which is being supplied during melting and also some energy being supplied during the process of vaporization, and this energy which is being supplied is a lot. Now the amount of energy which is absorbed or released, so this is the process happening in one direction. Alright, now if you proceed in the reverse direction, that is, let's start in the reverse, that is from vapor, let's go on to the liquid state. So that would result into liquid. So this is the vapor, then you will get liquid, and then you will get the solid. Okay, so in going from solid to liquid, you have to supply heat, and then from liquid to vapor you have to again supply heat. But from vapor to liquid, the heat is removed, and in going from liquid to solid, again, heat is again removed. So this process is called condensation, that is from vapor to liquid, and liquid to solid is called freezing. Okay, so during melting, now if you talk about solid to liquid, you have melting and freezing. So in melting your heat, you absorb heat, and in freezing you release heat. So that's why I'll take a generalized definition of these processes. Okay, so the amount of energy that is absorbed or released during a phase change process is called a latent heat. So whatever heat that you are providing over here is called latent heat. Now each latent heat has a definite name to it. Alright, so more specifically, the amount of energy which is absorbed during melting, okay, is called the latent heat of fusion, and is equal to the amount of heat, or you can say is equivalent to the amount of heat or energy that is released during freezing. Okay, and similarly, the amount of energy absorbed during vaporization, okay, is called the latent heat of vaporization and is equivalent to the amount of energy released during condensation. Okay, so you can say during melting we utilize the latent heat of fusion, and during vaporization we make use of latent heat of vaporization. So this is a concept which you should very well understand, because you will be using this a lot when you study the subject of refrigeration and air conditioning. Now, the magnitudes of latent heat. So let us denote latent heat by a letter capital L. Okay, so the value of, or the quantity of latent heat depends on the temperature or pressure at which the phase change occurs. Okay, so again, L is a function of temperature and pressure. So let us take some examples that at 1 atmosphere pressure, all right, the latent heat of fusion of water is equal to 333.7 kilojoule per kg. That means it takes around 334 kilojoules to convert 1 kg of ice into 1 kg of water. And similarly, the latent heat of vaporization, is equal to, you'll have around 2256.5 kilojoule per kg. So now these values are worth noticing down. Okay, so you can note these down values, because sometimes these are so commonly used values, sometimes they don't bother to give you these values, because they take it for granted that because we are talking about water, you know it. So just remember these values for the sake of solving the numerical questions. Okay. Now during a phase change process, the pressure and temperature are obviously dependent properties, and there is a definite relation between them. So this means that the saturation temperature, okay, is a function of saturation pressure. So this is how during a phase change process the two properties of T and P are related. Now the plot of saturation temperature versus the saturation pressure is called liquid vapor saturation curve. Okay, so let's draw such a curve for a very commonly used, or a very common pure substance, that is water, and you can have this kind of a curve for all the pure substances. Alright, so let's draw a curve. So these are the two axes. Alright, so this is how it goes. So this is the saturation temperature in degrees Celsius, and this is the saturation pressure in kilopascals. Okay, and then you have 0 over here as well, 200 kPa, then it goes to 400, and then to 600. Then let's increase the temperature, 50, 100, 150, 200, and so on. Okay, so as your pressure increases, okay, as your pressure increases, your temperature also increases. So it goes in this manner, like this. Okay, so this is how the temperature and saturation pressure are, varied. So it shows that the saturation temperature increases with saturation pressure. Now a substance at higher pressure boils at higher temperature. Now this concept is very commonly used in our daily cooking. So when you have your pressure cookers, this means higher the boiling temperatures means shorter cooking times. That is why you have high pressure vessels in which we cook food. Alright. So this finishes the video on the concept of saturation temperature and saturation pressure. In the next video onwards, we'll now look at the property diagrams for phase change processes. We'll look at the following property diagrams. The first property diagram we'll look at is the temperature volume diagram. The second one we'll look at the pressure volume diagram. The third one would be the pressure temperature diagram. And last but not the least, we look at a surface which is a combination of pressure, volume and temperature axis. So we'll talk about these three diagrams linked to the phase change of a pure substance in the next video.